Hello, everybody. Nice to see you again. And I guess it's the beginning of another week. I'm wearing a white shirt. I understand last time some people said that the white shirt was a bit too bright, but that's the thing I pulled out of my closet this morning. Now, if you're new to this live stream, I want to welcome you to a discussion of mathematics where we'll just talk about whatever questions people decide to ask. I know from experience that most of the people who are watching this live stream are thinking about algebra or geometry, and so we'll try to choose math problems that have something that I can talk about that is understandable to people who are understanding algebra or geometry. But if you're new here, what you'll see is that we kind of talk about lots of different things, and that's because math is very interconnected. And sometimes the questions will even be science questions, or questions from technology or engineering. I don't know what we'll talk about today. Let's see what people are asking. What do we have here? Let's go ahead and start. I see that a lot of people seem to be talking about white, in the sense that the shirt happens to be white. I guess here's something that might be interesting to you. That's something that I've been thinking about lately. You know what makes this look so bright? The reason this looks so bright is because the way that your computer is even storing how bright something is that there's a limit. There's an upper limit. And when you actually saturate that upper limit, when you get full, then unfortunately it doesn't know how to get any more white than that. One reason why this is interesting is because I was thinking about adding sound waves over the weekend, because one of the things that I'm doing right now is using sound waves to find the distance between people. And so it turns out that when you start to add all these numbers together, they reach a limit. Now, what's that limit? Let me tell you something about computers. And this something is related to math as well. Does anyone know how a computer stores numbers? Suppose I have a whole number, like an integer. Do you know how a computer stores whole numbers? You know, like the way I store a whole number is I might say, here's a number. The number is 15. Great, I tell you 15. And so now how does a computer store it? Yes, exactly. Eric Joe is right. The computer doesn't write down 1, 5. In fact, the computer stores it in binary. In fact, Grace Yan is talking about hex codes. That is a way of taking a binary thing and writing it down in a more compact way. But when we think about 15, the way that a computer would write down 15, Anonymous Cheetah has an idea. Well, the way you do this is you'd go and try to write it down, and there are some place values, right? So each of the places has a different value. This place is worth 1, this place is worth 2, this place is worth 4, and this place is worth 8, and this place is worth 16. And it's pretty obvious that I don't want to get any 16s. So I probably don't want to put another 1 in front. In fact, the way you do this is, well, there's two ways to convert into binary. Let me show you the two ways. The first way is to say, how many 16s do I want? None. Obviously none. It's too big. So I won't take any 16s. You can put a 0 in front if you want. If you put a 0 in front, that's just the same kind of thing as saying, well, don't take any of those. And when we write numbers, we don't always write zeros in front, but we can put that there anyway. Next, should I take any 8s or not? Well, I have 15 to make. I guess I should start picking up some 8s. And this should sort of feel like how you make change even. I mean, if I have coins, I don't know if anyone makes change anymore, but if you have a bunch of coins and you want to go and say like, here, let me give you 76 cents. You go and give quarter, 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 and then no more quarters, no more dimes, no more nickels. Here's a penny, right? We can go in that direction. And so that would be a 0 and a 1. Let's take an 8. The beautiful thing about binary is that you never take more than 1 of a place. And the reason is because if I was ever going to take like 2 4s, why take 2 4s? You can take an 8. Binary, you either take it or you leave it. So let's keep going. I see all these answers are coming. Once I took an 8, now it's like giving change. I have 7 left to do. Well, I should take a 4. Now I have 3 left to do. Okay, I take a 2. I have 1 left to do, and I'm done. So 15 is 1, 1, 1, 1. Did you know there's another way to do it? There's another way to figure out what 15 is in binary, and it's to go in the other direction. Some people are confused. What are we doing? We're trying to talk about binary and numbers. So suppose I have the number 15. I'm converting the number 15 into binary a couple of different ways. So suppose I have 15. There's another way to convert it into binary. The other way is to first say, here, let me ask you a question. if I have a number, and the number happens to be odd, do you know what is its last digit in binary? If I have any odd number, in binary, the odd number always ends in 1. And there's a reason for this. It's because if a number in binary ends in a 0, then it has 0 ones, and everything else it takes is even. Look at that. 2 is even, 4 is even, 8 is even, 16 is even, all the rest are even. So, in fact, if a number is odd, it ends in 1 in binary. If it's even, it ends in 0 in binary. So I'll go the other direction. I'll put a 1. Now once I put a 1 here, I can do this. There's a 1 here. There's 14 left to do. So now I want to make 14 out of these things. But I want to show you a neat trick. Do you know what happens if I ask a separate question? What is the number 10110110 in binary times 2? Okay, it's funny I'm writing a 2 here. I'll say 2 in base 10. It's just like multiplying by 2. Does anyone know how to do this? Is this thing horrible? Oh yeah, I want the answer in binary. At first, this looks like a terrible question. I have all of this nonsense. I need to go and, figure out what this is. That's a 1, this is a 2, that's a 4. Oh my goodness, I guess I could do this. A 1, a 2, a 4, an 8, a 16, a 32. I'm running out of space. A 64 and a 128. And you go and add all this stuff together. It's 128 plus, what's this? A 32 plus a 16 plus a 4 plus a 2. You add all these together, and when you're all done, you multiply by 2, and then you convert the whole thing back to binary. Does anyone want to do this? No. There's a better way to do this. The better way to do this is just to realize that the answer is just the original number shifted over by 1. Shifted over by 1 is this way. Why is that? Well, it's the same reason why in base 10, if I multiply anything by 10, I just add a 0 on the end. Why does that make sense? Because if I want a times 2, look, I don't want a 2, I want a 4. I don't want a 4, I want an 8. That's like saying instead of these, I want to put a 1 and a 1 there. And I don't want this 16 and 32, I want a 32 and 64. So instead of putting those ones here, I'll put the ones 1 over. And I don't want a 128, I want a 256. So I just push it. And somebody else pointed out 2 in binary is just 1 0. Oh, yes. If I just wrote the whole thing in binary, that would make sense. Because in fact, the way you multiply numbers, all these multiplication, like long multiplication, it works in any base if you just stay to the base. 2 in binary is like 10 in base 10. So if I want to do this, it's easy. If I do this, I just go and, okay, the hard part is I have to copy that over again. Oh, I know what I'm going to do. I'm going to write my equal sign down here, and then I do this. Watch. So easy. So easy. Why did I do that? The reason I did that is because over here, if I have 15 and I want to take 15 into binary, I already took 1 away, so I have 14 left. Now I need to know what is 14 in binary. Well, if I want to know what 14 is in binary, ending in a 0, then what goes here is just 7 in binary, half of 14. This is just 7 in binary. This is going to give us another way of converting a number into binary. We convert from the other direction. Yes, the question, what people are asking, what are we discussing? We're discussing how to convert numbers into binary. It's somehow inspired by a white shirt. I'll talk about that in a little bit. Okay? So now how do you convert 7 into binary? Well, is 7 even or odd? It's odd. If it's odd, then what should the 7 end with in binary? Odd numbers in binary end with 1. And since it ends with 1, I'll put a 1 there. Great. Well, if that was supposed to be 7 in binary, I took away 1. Now this is supposed to be 6 in binary, up to here. Ignore, pretend that doesn't exist. This is supposed to be 6 in binary. If that's true, if I ignore both of these, then what's left here is supposed to be half of 6, or 3 in binary. So now, using this working backwards method, what's here is supposed to be 3 in binary. 3. Is 3 even or odd? 3 is odd. Since 3 is odd, I'll go and put a 1 at the end, because odd numbers in binary end in 1. And now, if that's 3 in binary up to here, take away 1, this needs to be 2 in binary. If that's 2 in binary, then the part ignoring this has to be half of 2, or 1 in binary. What's left here is 1 in binary. Well, what's 1 in binary? It's 1. Boom, I'm done. So this is showing 2 different ways to do this. One way to do this is to go and do the 15 in binary by playing the game of making change. Go and take the biggest things you can, take as many of them as you can, and go forward. The other way is to go backwards and to go and say, what's my remainder when I divide it by 2? Is it even or odd? And you just go and fill it out that way. Both of these are legit. In fact, if you're writing a computer program, it is easier to do it the second way than the first way. The second way is a very easy computer program. I just keep checking my number modulo what I'm doing in my, I do my number modulo my base. So I'm just looking to see whether it's even or odd. That's what it's called technically. Okay, so we've talked about these things. This is binary. Binary is fun. And one of the things I was thinking about this weekend is that you may or may not know, but the way that sound files are stored in computers, a lot of them store it in what's called 16-bit format. And so in 16-bit format, there's a certain largest number that you can have. And that's a 16-bit number. So in the 16-bit format that the sounds use, the biggest number that they can express is something which has 16 zeros or ones. Except that they care about both positives and negatives. So they use sort of, okay, this is not quite true, but they sort of use one of the bits, sort of, to let you know whether it's positive or negative. That's not exactly what happens, but it's close enough. And so they have 15 bits in order to express a number, which is either positive or negative. And in fact, the biggest number that you can get in a 16-bit integer, signed integer, is what you can do with 15 ones. Does anyone know what that is? Does anyone know what 15 ones in base 2 is? I'll draw 15 ones like this. Almost looks like tallies, but pretend it's one big number. Does anyone know what this is? This is the biggest positive number you can express as a 16-bit sound file's amplitude. That's actually what this is called. Not amplitude, but the positive amount of this. Oh my gosh, how are you guys so fast? So some people said 32768. Some people said 16383. Now, I see some people are using powers of 2. And that's right. This is no fun. Don't go and try to add this. This is no fun to add. Do you really want to add 1 plus 2 plus 4 plus 8 and add them all up? No, you don't. Instead, we'll do this trick. If you were watching our live stream, you might have noticed that I think last week we did this trick. I don't know what this is. Let's add 1. Do you know what happens? If you add 1 to this, it's the same as 9999999 plus 1. It just starts to be a huge cascade. You know, like if I do the addition, I can even think of addition like this. This is fun. 1 plus 1 is 2, but 2 is 1, 0 in base 2. Oh boy, 1 plus 1 is 2, which is 1, 0 in base 2. And this just keeps going. And what do you get? You get 5 zeros here. You get 5 zeros here. You get 5 zeros here. And you finally carry the 1 in front. And so if you look at this, this 1 is followed by 15 zeros. And if you look at the pattern, the thing at the very, very end, this is worth 1, which is, that's how much the place value is. This is worth 2. This is worth 4. This is worth 8. This is worth 16. And if you look at the pattern, this is now going to be worth 2 to the power of 5. And it's 2 to the power of 5 when there are 5 zeros afterwards. And so that very first thing is worth 2 to the power 15. Because there are 15 zeros afterwards. And so the answer, people are asking, what is the problem? Oh yeah, well, in any case, we're just trying to find out what is this 15 ones in binary. The answer is the 15 ones in binary will be 2 to the 15 minus 1. So the original thing because if I add 1, I get 2 to the power 15. The original one is 2 to the 15 minus 1. And 2 to the 15 is a number which, if you calculate long enough, calculate often enough, it becomes something you see a lot. Not 2. It's 32,768 minus 1, which is 32,767. And if you go online and look at any of those video games that I programmed when I was in high school, this was a very important number because we were doing everything with 16-bit integers, and that was the biggest number you could get. So now, drawing this all around to the white shirt, the point is computers can only represent numbers up to a certain amount. And so this shirt looks crazily white because we've basically maxed out the whiteness. On the other hand, when you're doing sound, if you max out the sound level, then you make something called clipping, and then the sound kind of pops. If you're ever wondering why, it is true that if you play the sound too loud or you put too many loud sounds together, it makes a lot of popping sounds. It's because it basically went over the maximum number that you were allowed to put in. Okay, what can we do now? More questions. Oh, neat. Okay, so there was a question asking, how much money is there in the world? Oh, as much as you want. Well, not you want, but as much as people want, as much as the people who print money want there to be. You know, money is something that we just kind of believe is valuable. If suddenly everyone said, I don't believe in that money anymore. That's just a piece of paper. You give me that piece of paper, I won't give you any, I don't believe that I should give you anything. It's just a piece of paper. Then suddenly it doesn't mean anything. You see, the point of the money is that what the money is right now is it's sort of useful. If I have a dollar bill, I can go and take that dollar bill to someone else, I give it to them, and somehow they say, oh yeah, thank you, this is so valuable, this is a real dollar bill, and I can use it to do something else. But if at some point people said, what is this? I don't really know if this is valuable at all. If that happened across everyone, then suddenly that dollar bill wouldn't be worth much at all. And ultimately the question is, can you convert that dollar bill into real stuff? And if you can convert it into real stuff, it's valuable. It's actually, when we talk about money, you may or may not have heard about things like Bitcoin, or somehow this new kind of money could suddenly be worth an enormous amount, and then it could crash. And that's because it was all based on whether people thought that it was going to be worth something. Of course, there is real value in the world. The real value in the world is the stuff that you can produce, you can take out of the ground. I guess, then again, oil prices are negative nowadays, which is a different story. But somehow there's like real stuff. And as long as you have real stuff and you can connect the real stuff to some value, then that's how much the other value will be. But there's something called inflation. If, for example, the government decides to go and print lots and lots of dollar bills, it can do that if it feels like it. But then unfortunately, a lot of people are going to say, I'm not really sure this thing is so valuable anymore. I saved this dollar bill under my mattress, but somehow the US government just printed 50 trillion more of them. So my little dollar bill here is worth very little compared to the others, because there's just so many out there already. So that's the principle. The answer is there isn't actually a maximum limit of how much money there is in the world, because everyone could just make more. And ultimately what you want to do with math is to be able to understand how much your money is actually worth, I guess. And there are economists and statisticians who are always trying to figure this out. More questions. Shireen Chang, you asked a neat question. How do I not get glasses, even though I'm staring at a screen every day? I think the general recommendation is don't just stare at the screen. I guess in a YouTube stream like this, it's hard for me to tell you not to just stare at the screen. But see if you can make sure there's some part of your day that you're just thinking. Just thinking can be something that you even do with your eyes closed, or you can do it looking off into space. I think that helps a lot, because that helps your eyes concentrate on different levels of distance. In that sense, I guess when you go to school, you're able to look in long distances and short distances, and that's probably a good thing. So here's another idea. Here's something I did in college. I actually put my monitor really far away, just at some point. I was just like, I wonder if I can improve my vision. And so I just put my monitor really, really far away. I guess if you go and vary your monitor distance, maybe you can have that little bit of experience as well. But I'm not actually a doctor. I mean, I'm not a medical doctor. I'm not a useful kind of doctor. So I'm not sure that you should take my advice on that piece. What else can we do here? I'm looking at all of these different questions because I want to find something that might be suitable for this audience that we have here. Wow. Oh, we have all of these interesting questions that are in here. Okay, I saw a question that seems kind of interesting, and maybe we can talk about this. The question is, how do you aim in a game? I think I can make a mini lesson out of this right now. How do you aim in a game? Actually, there's a famous line in some movie. I didn't watch the movie, but I just heard there's a movie where there was, I think, something that was moving around, and somebody was trying to shoot the thing, and the person was just shooting and it was missing. And then somebody said, that's not how you go. You're supposed to shoot at where it's going to be, not where it is right now. So there are a lot of video games, at least the old school video games from a long time ago, where the bad guys would only shoot at where you used to be. They were not very smart. And so this question here of how do you aim in a game is, number one, don't aim at where the target used to be. Aim at where the target is going to be. But how would you do that? So let's suppose that I'm actually trying to figure out how to aim at where the target is going to be. All right, let's see. Is there a good way for me to try to figure this out? So, yes. So I actually now that I'm thinking about this, I'm trying to think of, is there an easy way to figure this out? So let's just play around with this and let's see if we can figure it out. Okay? So suppose that you are here. Okay? And suppose there's some target that you're trying to hit. I guess this looks like a target. But the target is moving. If the target is moving, does anyone have any ideas of what you should do? If you know the speed that the target is moving at, and you can do some kind of an aim, what would you do? You know, suppose the target is moving at that speed, and suppose that the thing that you are shooting at it moves at some other speed, and the other speed is faster. Suppose our speed that we shoot at is twice as fast. Suppose this is, oh, you know what? I have an idea. Let me start with something simple, okay? The thing I'm going to start that's simple is that the target is moving in that direction, and I have the ability to shoot something, but the thing I shoot goes at the same speed. Yeah, I guess sort of like dodgeball. Right, it's like dodgeball, okay? So the thing is that that's the target. I guess it's just the target is moving at that speed, and I have the ability to throw something at the target, but the target is moving exactly the same speed as the thing that I can throw. So, you know, I could try to throw this way, but I'm drawing the arrows of the same length, and since the arrows are of the same length, yeah, you're right, the ball is way faster, but we're playing against one of these people on this YouTube chat who likes to say, I am speed. So someone here can run as fast as the dodgeball, let's pretend. And let's just pretend that the speed that they're moving at is exactly the same speed that you can throw at. Is it even possible to catch this thing? Is it even possible to hit this thing? How do I choose what angle to aim at? So here, the important thing is assume your, I guess it's called a projectile, bullet or ball, let's be less violent, projectile moves at the same speed as the target. Does anyone have any idea of how you aim? Oh, yes. So I see that Debbie already has posted something about a video about football. Right, so I don't think I should make it go that way. If you throw it that way, by the time it gets there, the target has moved. But how far has it moved? Well, I could actually even draw that, right? If I threw this ball at the target, it will move that distance, which is the blue, and the target is going to move the exact same distance, which is the green. It will move exactly the same distance. And you will have been way off because you landed there and it got there. Useless. So what angle should you use? Does anyone know? Use heat-seeking rocket. Now, in this case, the heat-seeking rocket is a bad idea. You know why? Because in this case, the heat-seeking rocket is moving as fast as the other person. Maybe the other person is like Rocket Man or something. So if you use a heat-seeking rocket to try to chase a rocket that's moving at the same speed as the heat-seeking rocket is just going to get up behind and then turn around and then go and chase, but they'll never catch up. So that's not what you should do. The heat-seeking rocket doesn't work. What angle should you use? Obviously this didn't work, so I shouldn't aim at that angle. What if I try to aim at this, like go the same direction? Would that work? How would you know? There is actually a nice way. Somebody said 45 degrees. Somebody says use guided nuclear missile. But the problem here is that the target is moving at the same speed as your guided nuclear missile. So that wouldn't work either. And if you want to say, well, the way you deal with it is you just make the guided nuclear missile, kind of follow them and then blow up. Unfortunately, it'll probably blow you up at the same time. Somebody says 45 degrees. Somebody says make a triangle. Well, you see, it works like this. This target is going to move on this line. It's going to move on that straight line, and it's already decided that it's going to move in that direction. If I want to intercept the target with my projectile, I need to make it so that when I get to that point, they get there at the same time. So it's not exactly 60 degrees. It's not exactly 90 minus pi either. I'm trying to say I can do something geometrically. I want that the target has moved along this blue line the same distance as I moved to get there. If you can see, I want something that's symmetrical. I want to draw a picture like this. Let's draw another blue line. Well, blue is already taken. Oh, but I like blue. I guess I'll use blue. Let me draw another blue line. That's the line between us. Now what I want to do is I want to make something that's very symmetrical. So let me go and take the point halfway between us and draw a perpendicular line. Do you see what I'm doing? If I do that, then I want to take this and connect it to there. And now what I've just done is I found out that this distance, if I go along this line, the distance from here to there is exactly the same as the distance from there to there. Those are the exact same distance. And that's because of symmetry. This is not supposed to look like an equilateral triangle. In this case it does, but in other cases when it doesn't look like an equilateral triangle, you can still make this happen. And the important thing is if I just aim right there, then by the time the target gets there, oof, it gets hit right there. Let me draw another picture just to show how well this works. Call of Duty. So yeah, isosceles, that's the key word. It's an isosceles triangle. Let's try another example. So suppose I have the target here. And suppose the target is moving along this straight line. Nice straight line. And the target is moving on that straight line at a certain speed. And now I'm standing somewhere else. Now suppose I'm actually standing here. Oh, I need two hands. Okay, great. I'm standing there. And now suppose I can shoot something that's going at the same speed. Now it's not going to look like an equilateral triangle because I can do the same thing again. I go and draw the straight line between myself and the target. And you can even imagine doing this. Even if you were doing this in dodgeball, you could just imagine visualizing what's the point halfway in between you and the target, and then visualizing where this line, the perpendicular line, hits. That doesn't look perpendicular. I'm going to try again. That was probably like about the same as before, but we'll just deal with it. Okay? And then over here, this means that if I just go and aim in this direction, then these two are going to be the same length. They're the same length because it's an isosceles triangle. And since you have an isosceles triangle, then the two opposite sides are the two sides that touch. There are no opposite sides in the triangle, but these two sides happen to be the same length. So this is great. So the people who are asking, how do you aim? If you know that the speed of your projectile is exactly equal to the speed of the target, and the target is moving in a straight line, then this is what you can do. But now what happens if the speed is different? What happens if the speed is different from the speed of the target? Then what happens? Well, you see, it turns out that what we're seeing here is that there's a bunch of points in the world which are exactly the same distance from 2 points. That's what's relevant here. In fact, this line that I just drew, this is called the perpendicular bisector of these 2 points. That line's very important because that line is the same distance from those 2 points. So that's how I knew that if I've got these two people, well, I've got the person and the target, then I just go and see what are all the points in the world that are the same distance from the two, and I go and ask, is there any moment in time that my target hits that special magic line? Let's do it again. See, I've got my target. It's moving at some angle, but I don't actually care about that right now. I'm going to draw me. I'm here. And now there's a very special line, and that line is the perpendicular bisector. It runs between us, and it's perpendicular to the line between us. Looks kind of like a giant percent sign here, but this is called the perpendicular bisector. And this perpendicular bisector is the bunch of all the points which are exactly the same distance from both of us. Now, those are the points that are exactly the same distance from both of us, meaning if at any point the target would go and touch that line, then that place where the target touches the line, just looking at the angle it's moving at, if it was moving at this angle, the place where it touches the line would be a point that I can go and shoot for, and we'll get there at the same time. But now you're starting to see it doesn't always work this way. What if the target is doing this? Oh no, it's impossible. The target is doing that. There is no way I can shoot a projectile at it in order to catch it. And you can see it. It's because that target is going to move in a direction so that it never gets to one of these points, which is where the target and my bullet or my ball or whatever can get at the same time. So that's very interesting. That's how you can actually see how to do this problem. Now what happens if it's not that my bullet is the same speed as the target? What if your bullet is twice as fast as the target? Now what happens? Now if your bullet is twice as fast as the target, there's a different line that's important. It's actually not even a line. So here's a target, and here's me. Now I have a bullet that's twice as fast as the target. If my projectile... Oh, actually, I want to do it in a slightly different way. I want to draw these two things in a different position, but it'll be fine. The projectile is twice as fast as the target. Okay? I want to just draw these where I have some more space. So now I'm going to draw the target over here. And I'm going to draw me over here. Now I'm just kind of curious. What are all the points in this world? Oh, the world looks like this for you guys. What are all the points in this world for which the distance between me and the point is twice the distance between the target and the point? I want to draw all the points for which if the target was moving to that point in a straight line, and if my projectile was moving to that point in a straight line, then they would get there at the same time. I'll draw you one of the points. It is here. This point right here is exactly 1/3 of the distance away, 1/3 of the distance along. Do you agree? This point right here is a point that is exactly 1/3 of the way between us, and therefore the distance from here is exactly 1/2 of the distance from there. I'm trying to draw all of the points which are exactly twice as far from me as they are from the target. All points twice as far from me as from the target. What does that look like? There are two. Okay, good. So I see that somebody, the Pan Am guy, ooh, neat. The Pan Am guy says there are two. Can anyone tell me another one of those points? And maybe then you'll know why I redrew this picture down here. Can someone tell me another point which is exactly twice as far from me as it is from the target? Where might this be? I'll give you a hint. There's another point that happens to be along this line. There's another point that's exactly twice as far from me as it is from the target. I just go and take this, and that's me. I kind of reflect me over the target, and I find the point on the other side. Yes, reflection. Thank you very much. You said exactly what I wanted. Reflection. This point. And so the important thing about the point that I just drew is that it's supposed to look like the point here is like the mirror image across this of me. Actually, it doesn't look far enough. I'm going to move it a little bit farther. I'm not sure that even moved at all, but let's just draw it here. So it's basically like this thing, this target was a mirror, and so this distance plus this distance is of course twice of this distance. Okay. But now, there are actually more points in this world which are exactly twice as far from me as they are from the target. It turns out that I can draw something that connects them all. And here's a hint. This is what it looks like if your job is to draw all the points in the world which are the same distance between me and between the target. If that's the case, if I want to do something which is like, it's twice as far from me as it is from the target, well, I guess it should start off looking something like that, right? Can you imagine this? It's sort of like there's all these points. All these points are supposed to be twice as far from me as they are from the target. And you notice that it's not a straight line anymore. It kind of curves, but it has to get all the way to the other end. How could it get all the way to the other end? What would this look like? If I want to draw all the points in the world which are exactly twice as far from me as they are from the target, I need to kind of start off like this, and I need to get all the way over to there. It's a circle! Time W.W. Brody. That's right. It's a circle. This circle is all of the points which are, okay, the circle is not quite right. It's not supposed to be lumpy like this, but it's supposed to be a circle which is symmetrical across the line that goes between us. And every point on this circle is such that it is twice as far from the target. It's twice as far from me as it is from the target. This is amazing. In fact, this has a name. This is called a circle of Apollonius. Now the hard part is spelling circle. No, that's the easy part. Apollonius is the hard part. Maybe some of you who are on the computer can help me. How do you spell Apollo? Is this right? I always have trouble spelling Apollo. Are there two P's? Are there two L's? Are there two P's and two L's? I'm not sure. But it's going to be something like this. It's a circle of Apollonius. And the circle of Apollonius is all of these points, which are exactly like the ratio of how far away the point is from me compared to how far the point is from the target. That ratio is constant. And this is the circle of Apollonius, which corresponds to a ratio of 2. Actually, the circle of Apollonius that corresponds to a ratio of 1 doesn't look like a circle at all. It looks like a straight line. You see, because there are all these different circles. You could imagine that this is the circle called my projectile is twice as fast as the target's motion. And it looks like this. If my projectile is 50 million times as fast as the target, guess what my circle looks like? It looks like that. And that makes sense. If your projectile is 50 million times as fast as the target, you could just aim at where the target was. It's probably close enough. Does that make sense? So there's like this is a circle of Apollonius if I'm asking what are the points where the ratio between distance to me and the distance from the target is like 50 million. On the other hand, if I happen to be using a really slow bullet, if the bullet happens to be such that my bullet is half as fast as the target, well then, what are the points that are such that the distance to me is half of the distance from the point to the target? It would be just the other circle of Apollonius going around this way. So there's all these circles. Now here's the relevant thing. You asked, how do you aim? Here's how you aim. What direction is the person moving in? Oh, by the way, we can already draw this circle. The way you draw this circle is you draw that point and you draw that point. This point I got with a ratio, right? I said this point is 1/3 of the way along, so I could draw it. This point was the reflection, so I just put that point there. And I just made a circle with that diameter. Now, let me tell you how to aim at the target. Suppose that the target is moving at this speed. Can anyone tell me where I should aim? This is actually pretty cool. Where should I aim? The target is moving at that speed, and I know that my projectile is exactly twice as fast. So what should I do if I know that the target is moving in that direction? Aha! Temp ID says, just see where the line intersects. Let's use another color. Where the line intersects the circle of Apollonius. Bam! Right there. I should just aim there. This is really fun. This is actually showing how a question that looks like it should have been impossible. Oh yes, I didn't prove to you why it's a circle. That is something which is easiest to prove. If you go and use, actually it's pretty easy to use coordinates. If you use x's and y's and you write distances in terms of square roots and some squares, you can actually work this out for yourself. I won't go into that. There are also other proofs of this that don't even require writing down these squares and these x's and y's. But that's not what I want to hit today. Instead, I just wanted to show you this is a very interesting fact that you can have this circle. And in fact, if you just go and draw this, you just go and look at where that line intersects the circle, and boom, you just aim at that particular point on the circle. And just as the target gets to that point, so does your projectile. This is neat. You just need to know the ratio of the speeds of your projectile and the target. Go and see where they intersect based on the target's direction. Aim, and you're done. There's only one catch here. What if your target... one thing here is like, look, if my projectile is faster than the target, I'll always have a point that works. If my projectile is slower than the target, then my circle of Apollonius might be around me. And there might be no point where this thing hits the circle. That just means you can never catch it. Okay, well, thank you for that question. This was actually quite interesting. I found this quite interesting to think about. And you know, I think this is actually a legit explanation. And if you thought that maybe such a question was hard to answer, well, it turns out that this geometry is really useful. And this particular kind of geometry is stuff that I didn't learn in a geometry textbook because it's not really in the American standard geometry curriculum in high school. On the other hand, if you like playing with math contest problems, this kind of a problem appears in the American High School Math Olympiad problems, the ones where you go and write proofs. Okay, what else can we talk about? Aha. So I'm looking at all of these things. Sophie Chang asks the question, why does airplane food taste so bad? It's an economics problem. This is also, you asked me about, like somebody asked me about, what is money worth? Well, here's the deal. If you are on an airplane, what are your options for food? Well, you have one option called the food that they have. You have another option called what you brought on the plane. But let's suppose you brought something on the plane and you don't intend to eat for 3 more hours. That is called the option of cold food that you got in the airport and brought onto the plane. What are the other options? Oh yes, there's the option that's on the plane. So in that case, what are you going to choose? There isn't really much. Oh yeah, there's another option called just don't eat. And I guess you could do that too. But ultimately, you don't have enough choices. And so since there aren't enough choices, they only have to be as good as whatever your alternative is. So in some sense, the food that's on the plane is sort of competing against the food that you brought in from the airport and has been waiting and sitting for like 3 hours. Or the other thing they have to compete against is maybe there's another airline out there. Maybe there's another airline company, and they have really good food. And if that's the case, then maybe a lot of people will say they just want to go to that other airline, and then you'll lose business as your airline offering like this food that you don't like. Well, the issue is that somehow if you ask people, would you rather have a cheaper airplane ticket or would you rather have better food while you're on the airplane? Most people would say, I'll take the cheaper airplane ticket. And so this is actually all answered by supply and demand. It's just simply that there's just not enough demand for there to be great food on the plane. And, there's not anything you can do to try to get a better option. This is also why sometimes if you go and I guess if you look at a university campus or the places where there are food places to buy dinner, it's somehow the more convenient something is, oftentimes the less good it is because they have something else that's already making up for the fact that the food quality is not as good. All of these things you can understand with math. Other questions? Lawrence San says, I just drink the soda they give you for free. Yes. Yeah, actually, somebody also mentioned, it is true. The atmosphere does change in the air. Although inside the airplane, they try to pressurize it. So the way that the Earth is, right, you have something called air pressure. And what's air pressure? Air pressure is the weight of a lot of air. There's a lot of air. It's all sitting up here. It's like all this air is stuck on top of us, and it's held down by gravity. And of course, if you go really, really, really high in the atmosphere, the air pressure is less. There's like less air like squashing down on top of you. And so when you go and fly in an airplane, in fact, the air pressure is less. You may also have noticed, if you ever take these very, very long flights and it tells you the temperature outside, has anyone noticed what the air temperature is outside on an airplane? The air temperature outside in the airplane, like outside of the airplane when you're at cruising altitude, is not like 60 degrees Fahrenheit. In fact, the air temperature when you're outside is basically something like -40. Okay, that's like the air temperature outside the airplane. And so inside the airplane, it's really cold outside and there's low air pressure outside. So in fact, the airplane is already climate controlled. They already have something that pressurizes the cabin. So it makes it like a normal place that you could breathe. It's not some low pressure thing where there's not enough oxygen for you to breathe inside the space. And at the same time, it's a warmer place. So it is true that it's weird up in the air. However, if someone really wanted to have super gourmet stuff in the air, they could. It's just not in demand. By the way, why did I write -40? -40 is fun. I didn't tell you whether it's Celsius or Fahrenheit. You guys should be complaining. Let's try to convert. What if it was -40 degrees Celsius? Let's convert this to Fahrenheit. What is this? What's -40 Celsius in Fahrenheit? Well, I need to convert, right? So what do? For Fahrenheit, it's a linear relationship. So I have to take the 32. Well, I guess a lot of people write it as 9/5 C plus 32. Right? So let's do it. What happens? So if I go and plug this in, I get 9/5 of -40. What's 9/5 of -40? Oh, you guys are quick. Okay, 9/5 of -40. 5 times 8 is 40. So 9 times 8 is 72. -72 plus 32. Oh boy, it's -40 again. So -40 is a special number. -40 Celsius is the same as -40 Fahrenheit. And that's why when I wrote the -40, I was like, I don't even need to tell you whether it's Celsius or Fahrenheit. Both of them are exactly the same. And so this is kind of cute. And maybe someday it'll be useful if you ever decide to go to a really, really, really cold place. Okay, more questions. Andrew Chow asks, how do you find so good explanations for people's questions? To be honest, they're just good questions. And if you want to know what I was doing, when you asked me the question about like these like different like aiming, how to aim, I actually didn't know the answer when I started. I was just like, I think maybe it might have something to do with like circles. But actually the other part was, I was just curious. I was like, that's a real question. I don't know the answer. I want to know what the answer is. What could I do? And I just kind of drew some stuff. So I think the thing I'm trying to show through this is that a good question is usually what makes a good answer. And so the fact that you guys are asking some pretty good questions helps a lot. What else can we do here? DWW63 asks, how common is my birthday? Now this is an interesting question. You see, the answer at first might be, well, there are 365 days in a year. So that means your birthday is 1/365 chance. Like if you have a particular birthday, the chance someone else has the same birthday is 1/365. But this makes this has some problems. One of the problems is that it doesn't take into account that there might be like more people who are born at certain parts of the year just due to the fact that the world is different at different stages of the year. Sometimes at some stages of the year, there are certain things going on in the world, and sometimes there aren't. The world is seasonal. So in that side, I don't know how to answer that question. On the other hand, what I'll say is that there's also the leap year issue. So how would you deal with the leap year? So maybe let's think about that, because I don't know how to answer the issue. Well, not that I don't know how to answer. It's like that would require a lot more details to answer the issue based on, how often different things happen during the year. But what would you do? Would you say it's 1/366? So let's just pretend. Let's pretend that what's going on is that everyone. Let's pretend that everyone is born at like at a uniform rate, meaning that at any particular time during the year, there's like the same number of people being born. Then the question is, should it be 1 over 365 or should it be 1 over 366? What do you think? So you need to know what a leap year is. A leap year is that every 4 years you have 366 days, and every other year, not actually every other year sounds like every other year, but I mean like everything that's not a leap year is 1 over 365. So what do you do between this 1 over 365 and 1 over 366? It's not fair to say that the answer is 1 over 366 because it's less likely anyway that you were born on that leap year. Sorry, it's less likely anyway that you were born on that leap day. So in fact, the correct answer is this 1 over 365.25. And the reason is because, wait, actually, is that right? Let me think about it. So let me just check this out. This is the way that I'll do it, okay? Here's how I check this out. So I think the answer is 1 over 365.25, but let's find out. The way I would do this is I would say, let's suppose that I have a 4-year period and people are just being born, okay? And I choose a 4-year period so I get a leap year, so I get a leap day. So in this 4-year period, I have like, this is not leap year. This is not a leap year. I'm just drawing a timeline. My timeline is supposed to mean that like where you're born is like something along this line. Like there are lots of buckets. Actually, each one of these things, this is again a not leap year, and therefore the last one's going to be a leap year. But I'm imagining that I'm splitting this into like lots of buckets. The buckets are like 1 per day. So this has 365 buckets. Buckets are what you use when you think about computer science sometimes. It's like I have buckets and I'm storing stuff in the buckets. Here what we're storing is we're sort of saying I've got all of these different days, and each of those days has people who are being born. Okay, so let's put that there. And let's keep going. Not leap, not leap, not leap. And finally the last one is actually a leap year. A little bit longer. And on this leap year, this one actually has more buckets. This one has 366 buckets. Okay, so now if I wrote all of this thing down, I've got if I wrote all of these down, I have like all of these different buckets. Now, the question is, what's the chance that someone else has the exact same birthday as you? So the question is, who are you? Oh, that's an interesting question too. So now we actually have to go and do something with this probability, where I need to state it more carefully, because if you ask like what's the chance that someone has the same birthday as you, if you already know your birthday and you know that your birthday was February 29th, then I know that the chance that someone else has the same birthday as you is a lot less. Because if you are going to have a birthday of February 29th, the chance that anyone else has the same birthday as you is going to be one of these days' works divided by the total number of days that we have. Yes, that's correct. If you ask, let's answer it this way, okay? Actually, this might help a lot. So let's use a white. If you were born February 29th, then the probability anyone else has the same birthday is equal to only one of those days works out of all of these buckets. It's 1 over 4 times 365 plus 1. And I don't actually care too much about what the number is. I just want to say that's how I do it. The reason this makes sense is because, again, I have to think about what's the linguistics of how this question was asked. If you said, what's the chance that someone has the same birthday as me? If you're saying that you already know what day you were born, and if by the way, the day you were born was February 29th, well, then that's what you do, right? You just calculate this, I'll just calculate this, and I'll tell you highly unlikely. On the other hand, if your birthday was not February 29th, if you weren't born on February 29th, then the probability that anyone else has the same birthday as you, well, there are now 4 options in here. There are 4 options that will work. 4 days out of all of this time. And the probability is 4 out of 4 times 365 plus 1. Okay, so now I'm glad I'm doing this slowly, because that means the answer I gave originally is wrong. You see, originally I gave you this answer. This answer is 1 over 365.25. And so it's a funny question. It's like, if you who are asking me the question, well, you know what day you were born. And if the day that you were born is one of these that's the more normal ones, then the answer I gave you was correct. On the other hand, if it turns out that what you told me was, if you told me something, not if you told me something, if you asked the question and you were actually born on February 29th, then my answer to you would have been wrong. Because if your birthday was actually February 29th, and you know what that is, then of course the chance that anyone has the same birthday as you is that. So there are actually two different answers here, depending on what was your real birthday. And that's if the linguistics of the question is such that it is, you're just asking me, what's the chance that someone else has the same birthday as me? Me meaning you, I guess, because you already know that. But can I write another question then? I could also write another question which lets me give one answer which is independent of, what your situation is. I can ask a different question, which is to say, if I pick one person at random and then pick another person at random, what's the chance that two randomly chosen people have the same birthday? That's a different question now, because I'm going to pick both randomly. Do you see the difference? You originally asked a question where you were the one who was asking me the question, and you know your birthday. So the answer to you is one of these two, depending on what your case is. Now I want to remove the you part, and I want to say, look, I will just pick two people, and I want to know what's the chance that they have the same birthday. Well, how would I do this? If I want to do this, I combine these probabilities. So what I'll do if I wanted to solve this problem of asking a separate question, which is, what's the probability of picking two uniformly random people? Uniformly random means like they have the birthdays which are equally distributed over time. Uniformly random people, same birthday. I could do this by saying, let's pick the first person first. When I pick the first person first, I either get the first situation or the second situation. And so I'm actually going to multiply some probabilities and add them. So the way I would solve this problem is I would go and say, well, what's the probability that the first person I pick has a birthday that's February 29th? It's equal to the probability that the first person is February 29th, and the second person, same, plus the probability that the first person is not February 29th, and the second person is still the same. So to do this, I would go and find the first one, which is what's the chance that the first person is born on February 29th? Well, I already wrote it. It's this thing. It's one day that works out of this entire 4 years. So it would be that thing times itself. And then what I add it to is 1 minus that thing times this. Let me write that down. So my answer is going to be equal to, it will be 1 over 4 times 365. I'm going to call that n. 4n plus 1 squared plus 1 minus 1 over 4n plus 1 times 4 over 4n plus 1, where I've just done n is 365. Is that okay? So I just said I don't want to keep writing 365, I'm going to call it n. And so what's the chance that the first person was born on February 29th? 1 over 4n plus 1. What's the chance the second person has the same birthday? Well, I just calculated that. If that person, if one person was February 29th, the second person, same birthday is that probability. Second piece is, well, what's the chance the first person's not born February 29th? That will be 1 minus the chance of being February 29th, times the probability that the second person has the same birthday, which I already calculated. It's this 4 over 4n plus 1. Now let's put it all together. What is this? I'm going to write that on the next screen. 1 over 4n plus 1 squared. I'll write it like this. And then plus this piece. 1 minus 1 over 4n plus 1 times 4n over 4n plus 1. Okay, I guess if I need to do this, let's just put it together. This is now algebra time. I'm going to write 1 over 4n plus 1, whole thing squared, plus this 1 minus 4n plus 1, it's 4n plus 1 over 4n plus 1 minus 1 over 4n plus 1. I'm doing it slowly just to show you something beautiful happens. Over 4n over 4n plus 1. Okay, we're going to get there. 1 over 4n plus 1 squared. And then plus, over here, I actually can write the whole thing over 4n plus 1, 4n. Oh, that's nice. We're going to square that, because I'm multiplying it by itself. And so if I join everything together, what I get is I get a 1 plus 16n squared divided by whatever the bottom is, which is 4n plus 1 squared. Okay, so somebody said cancel. So I don't want to leave it as 1 over, I don't want to leave it, the 365 lying around, because it's a lot easier just to deal with it this way. And so now I just need to plug it in. In fact, this is not nice to plug in. I mean, this is not nice to simplify. It doesn't simplify any further. I actually can't divide this by anything further. So at this point is when I'd plug into a calculator. You know, we can plug into a calculator if we want. And what do you get? Does anyone know what you get? If you plug this into a calculator, so I can tell you approximately what you get. Can I? Yes, I think I can. Right. But now I'm a little suspicious. Something is wrong here. Yes, it's time to go. That's true. You guys feel free to go if you want. But now I'm curious. So if I got on the question, I want to know the answer. And now I'm not super happy with this answer because I'm getting something which is strange. Is that right? So this thing plus this thing, and then 1 minus it times that. Yeah, that should be right. So if I go and add these things together, 4n, okay, that makes sense. No, something is very, very fishy in here. All right, who can see a mistake? Because, hey, good. It's not 4n, it's 4. Okay, that's right. Because something here is very, very fishy. Oh, good. Okay, this is a 4, not a 4n. Much better. And the reason is because I knew that it didn't make sense. The probability shouldn't be close to 1. These are just 4s. If those are just 4s, then this particular piece, let's change the squared, the bottom has the squared, and that's going to just be 16n. This is much better. Good. And if that's 16n, then I don't have the 16n squared. Now I'm happy. So now we just need to plug it in. And so if we go and plug this stuff in, what do you get? Is there anyone here who has a calculator? We can try to figure this out now. What is 16 times 3? What is 1 plus 16 times 365 divided by 4 times 365 plus 1? Whole thing squared. This is not going to be a nice number. It's not going to simplify in a nice way. And if somebody wants to plug it into a calculator, we'll find out what it is. It's going to be something. And, you know, what I'm most interested in is what is 1 over it. So I'm actually quite curious if anyone wants to plug in this. I want to invert the fraction. So I want to really know what is 4 times 365 plus 1 whole thing squared divided by 1 plus 16 times 365. Is there anyone who can help me with this? I want to approximate this. Because as you can see, I'm not actually I'm not a fan of the calculators. I just want a number at this point. Okay, so it's 0.0027, that's right, but I want to know what's on the bottom. I want the reciprocal of that. The reason I want the reciprocal of that is I want to compare that with 1 over 365.25. Because that will be interesting. And I have a suspicion it's less than what we expected. So let's put something there. What would be 1 over your answer? So here I'm waiting. 942 doesn't sound right. You know, like the answer should be very close. 365.4 something is what I see. Here, this came from the audience. So I hope it's right. But we have some number here. And what the number here is you would just put a 365 where n is, calculate the whole thing, and then flip it over. And when you flip it over, you'll get what we put here. And that's quite satisfying. It's like somehow, what's the chance that you have the same birthday as someone else? Well, it's close to 1 over 365, but not quite. And this would be this is how you deal with the leap year. And this would be the situation if we were picking two different people separately. Okay, well, so this was our live stream for today. So this was our live stream for today. Again, the accuracy of this last number is dependent on what people have given, and maybe it's right, maybe it's not right. But what you can see is that's how I think through things. That's how you can think through things. This is how you can, make mistakes, fix them as you go, and hopefully eventually figure out the right answer by saying, no, that answer was too close to 1. That's impossible. It can't be that high. If you liked what you saw today, please tell other people, because this is the chance that we have during this particular difficult time to try to reach as many people as we can, to show them, what math can lead you to. And today we've talked about a lot of different things, and hopefully you've learned as much as I've learned, because I didn't know the answers to all your questions when you started either. I wish you all the best for the rest of this Monday, and I'll see you tomorrow. We'll be back at 4 o'clock p.m. Eastern Time tomorrow.